My name is Blanca Tobar. I will be the chairman. It's a pleasure for me to be here in this session. Just as introduction, I was a student here in bioelectronics last century. And well, it is always my pleasure to be in these sessions and see the advances in biomedicine and biomedics. We are going to have 6 presentations. Some of them are going to be here, presential, and some others online. And we are going to start with our first presentation, which is called Design, Development, and Experimental Testing of a Neurostimulator for the Tibial Nerve in Wistar Rats, and presents Ramon Cortina.
Thank you. Hi, my name is Ramon Cortina. I am from the Bioelectronics section of the Electrical Engineering Department here at Simvestab. And I'm going to present the work, design, develop, and experimental testing of a neurostimulator for a tibial nerve in Wistar rats. So, as an introduction, in a lot of research, laboratory rat models are used to perform some investigation about new treatment, for example, for overactive bladder or urinary incontinence. So, in this treatment, some research will be used electrical stimulation, such as neurostimulation. So neurostimulation is a type of stimulation that use voltage and current that they apply to the nerves. So it's different to the functional stimulation because functional stimulation is for the application over a group of muscles. So in this case, this work is centered in a neurostimulation device. So some device need to use different waveform to apply different type of stimulus. So some device could be delivering a monopolar square wave or bipolar square wave or any other type of waveform. Neurostimulation in animal model is particularly used to test some pharmacological or drugs, for example, for new treatment like a surgical procedure. In a combination of this type of new treatment will be show more efficacy in the treatment of some disease. So, however, this type of device will be expensive. In some case, need to be exhibit elevated power requirement, like a special power source or another additives that need to be used to work in some research. So, in some cases, these devices are expensive, and for some laboratory research, it's difficult to buy some of these devices. So the object is this work is present the design and develop an experimental neurostimulation for the application in the percutaneous or direct stimulation in the tibial nerve, with the objective of study the operative bladder in a model, in an animal model like the rat of laboratory. And this device has 5 principal blocks. So the principal block is the pulse generation and control signal. In this block, we use a microcontroller to generate the pulse. This pulse serves like for the generation of the waveform for the stimulation. Another block is the pulse invert circuit. This circuit is used to invert the pulse. In this case, our device only uses a single power supply, because some devices use a dual power supply to generate negative stimuli or positive stimuli. And we have a voltage to current source. So with the magnitude of voltage, we can use a voltage to current source converter to change the magnitude of the voltage to a magnitude of current. And of course, we use a H bridge to change the direction of the current through the load, or in this case, through the tissue. And we use a power source. This block is not only for the battery, we use a battery of 9 volts, but this block is a sub-circuit that we use to connect or disconnect the load from the high power supply. So the pulse generation and control, for the pulse generation and control, we use a microcontroller. So with the microcontroller, we can define the frequency, the amplitude and magnitude of the current, and we can control the duration of the pulse. So we use the digital output of the microcontroller to generate different waveform that we can apply to the animal model or another type of load. And we use a voltage source to control the voltage that we use in the voltage to current converter. So with the same pulse that we produce with the microcontroller, we produce the pulse of the current that circulate through the load. So the block of the pulse inverse circuit is a circuit that allows us to change to switch the voltage to current source. So with the same pulse that we use in the microcontroller, we can generate a pulse, the pulse of the voltage to current converter. And we use two N-type MOSFET that we can switch with the B1. B1 is the microcontroller pulse. And with this pulse, we can activate the M1 gate of the MOSFET. And in this case, in the node B1A1, we have the pulse that show in figure 5, letter I. And in the other MOSFET, we have 0 volts for the inversion in the A1 node. So with this circuit, we can switch the voltage to current converter. So we use a conductance amplifier to control the magnitude of the current. So we use the pulse that generate here in this subcircuit, and B4 represents the pulse that we use. So this pulse, we convert this pulse to a magnitude of current. We use the resistor R5 to sense to sense the drop voltage through the resistor. And with this, we can create a feedback to the amplifier to control the current through the load. So with the pulse, we activate N-type MOSFET, and with the activation, we can generate the circulation of the current through the load and through the R5. So the equation that defines the current through the load is the equation number 1. So if we apply a voltage of 0.1 volt over the B4, and with a resistor of 1 kilo ohm, we can program a current of 1 microampere. So the power supply block is a subcircuit that controls the connection or disconnection of the load to the high voltage. In this circuit, we use 9 volts, but some application requires high voltage, like 300 volts, for example. And we can use this circuit to connect or disconnect the load. This is a security. This is a characteristic of security for the animal model or for the research, because could be exposed to the high voltage. So, for example, B2 represents the microcontroller pulse. It pulse activate the gate of entry and MOSFET. And when activate this gate, we generate a flow of current through R1 and R2. So the drop voltage through R1 generates a voltage that can activate the gate of PMOS. So with this, we can connect or disconnect the load from the high voltage source. So if we take all these components and we can create the H topology, the H brick topology, and we can generate the different waveform like this. Figure 7 shows the bipolar stimulation waveform that we obtained from a LT SPICE simulation. So to generate the positive pulse, we activate B2 and B5. At the same time, B3 and B4 are turned off. And with this, generate the flow of current in one direction. And in other direction, we need to turn off B2 and B5 and activate B3 and B4. So with this can create different waveform. For example, here people are waveform. So with this simulation, we implement it all this. We implement the circuit with real components, and we test it with some current, with some program current. For example, with a voltage of 20 millivolts, we expect to obtain 20 microamperes. In the best case, we obtain a variation of 10%, and in the worst case, we obtain a 10% of variation in the current that we program, and in the best case, we obtain 1% of change in the current, 1% of variation in the magnitude of the current that we program. So with this, we implement the device in an experimental protocol, and we use four Wistar rats with a weight between 250 and 300 of grams. The animals were moved to a locate with a 2-hour light and 2-hour dark cycle, with a lipidum access to water and food. And we use an anesthetic by an inhalation of isoflurane and one combination with isoflurane and oxygen, 3% of isoflurane for the induction and 1.5% for the maintenance. Of course, all procedures were conducted at the Simstat Animal Production and Experimental Unit and in accordance with the institution guidelines. So in the figure 9, we can see the experimental setup. For example, for the percutaneous tibial stimulation, we use two stainless steel needles that we introduce over the skin to into the muscles to the nerves. In this case, the tibial nerve. And we apply monopolar and bipolar stimulation, and we evaluate the response of the animal. For the direct nerve stimulation, we put the two electrode of platinum over the nerve, the tibial nerve. For that, we use a surgical procedure to access to the tibial nerve, and at the same time, we use two electrodes to obtain the electromyography recording from the urethral sphincter from the rat. And for example, the response that we can obtain from the device. In figure 11 shows the simulated bipolar stimulation waveform that we obtain in the LT-SPI simulation. And this is in figure 12, the bipolar recording that we obtain from the recording of the animal model. We can see that the waveform is near to the same at the waveform that we simulate with the LT-SPICE. So if only we take some extract of this waveform, we can see that the bipolar waveform. And in this case, if only take a pulse, we can see that the behavior have some capacitive behavior because the impedance of the biological tissue. And this is a video recording of the application of the tibial nerve stimulation over the animal model. In some paper, researching report that the activation of some tools on the animal express a correct nerve stimulation. So we can see that the device could be delivering bipolar monopolar stimulation and activate the food of the animal. And as a conclusion, this work presents the design, fabrication, and implementation of a device that will be delivering monopolar or bipolar stimulation. In this case, we use a 9 volts battery, and the device is electrical isolate for the research and the animal model. And we perform in vivo testing on Wistar rats. And with this, we can demonstrate that the system could be worked with a specific current and magnitude of the voltage. And we apply percutaneous and tibial nerve and direct nerve stimulation, and we show and we confirm that there is a different magnitude to to obtain the same response with a percutaneous or direct stimulation. So our circuits are built with a commercial component. So any other research could be used this circuit to implement another device, for example, for neurostimulation. And the device is used in a future world to perform some neuromodulation experiments with the objective of studying the operative bladder in an animal model with urinary incontinence. So that's all. Thank you for listening.
Thank you, Ramon, for your presentation. Do we have any questions here in the room? Yes,
And
please.
why do you use female rats instead of male?
Because we have another protocol experiment, and in the protocol experiment that we use, this device, is more easy to access to the urethral sphincter in the female rat, that in the
Male.
that in the male. So the surgical procedure is more easy because you practice the surgical, and it's easy to find the urethral sphincter than the male rat. It's more difficult because you have another organ. So in this case, we are using female rats.
Yes, because it's very curious because the most of rat models is in male instead of females.
So it was, you make another experiment and
Yeah.
you take the same rat for the
Yes,
for
yes.
testing your device.
We use this device to implement neurostimulation, and we are going to evaluate the response in an operative bladder animal model. So the laboratory experiment is continuously in this case.
Okay. Thank you. Any other question here in the room, please? Yes, please.
Ramon, part of the motivation that you introduced in that section is that some devices are highly in cost, so you design your own instrumentation for this experiment, right?
Yes.
How do you know that the electrical and safety protocols were taken account, or that your device is at least near to those that are certified for this kind of study?
The device is a prototype, so we need to perform more tests. So we can say that device is commercial, because we need to test it in another with another type of test. For example, in this case, we use an animal model because we can perform some validation with resistors or capacitive loads, and we can measure for example, the behavior of the components. In this case, we use a commercial component, so it's easy to go to the electronic store and buy it. But if we find to prove that the device could be safety for any person, we need to use components with a test that says that the component could be used in a medical procedure, for example.
But perhaps the fact that you're reaching the goals that is part of the hypothesis of your research, maybe the motivation should not be that you're developing a low-cost device, rather than you are designing a device that is adjusted for your kind of study. Can you see the difference?
Yes, but another motivation of the development of this device is in some laboratories it's difficult to obtain some resources to.
I agree.
So this is an option for any research that could be used for perform some neurostimulation experiments.
Just keep in mind that could be controversial.
Yes.
Low-cost, high-cost is
In fact, the use in animal model is a controversial.
Yes.
So we need to have carefully with the application that use this device or the animal model.
Thank you very much.
Thank you, Doctor.
In the same sense, I have another question.
Yes.
Did you take into account the norms, the
Yes.
standards for your device?
Here in Simplestar, we have the biotech, the unit of animal procedure. So we have number, we have a approved protocol to work with these animal models. So in any moment, personnel of the biochemists help us to perform this procedure, and we take carefully with the animals. So our procedures are supervised by other type of personnel.
Yes, that is in case of the rat.
Yes.
But for the device, in the design of any electronic device, you have norms and standards.
Yeah.
So do you have those norms and standards? I mean, do you know which ones are you taking into account?
We check some standards for the I3, for example, for the current that we can use to perform a stimulation over an animal model specifically, and the current that we are using to perform this experiment is not more than 1 milliampere. So we take carefully about the standards, but it is a prototype, so we need to perform more investigation and more research about the behavior, in this case, in animal models.
Okay, thank you. Thank you. Well,
I don't understand really well, like how big or how little it is the circuit, and if it has a battery, or how is it that it's controlled, or how it can be charged.
In this case, we use a 9-volt battery. It's a commercial battery that is not any special. So I don't know if that is.
Yeah, what I don't understand is that we saw that it's the leg and it's open and it enter
Why
12,
slice? What slice?
12. Like, I would like to understand how is it the circuit, or how is it the battery, or how I thought that they put all of the circuit inside, but is it not? Or how is it? Yes,
no, I mean, the electrodes are touching the leg, but not the whole circuit. The whole circuit is something external.
but it's open, meanwhile it is stimulated. Or how?
Did you make a surgery to introduce the electrode?
Yes. We use a surgical procedure to introduce the electrode, but in the direct stimulation. In this case, we need to expose the nerve and put the electrode over the nerve to perform direct nerve stimulation. And in the case of percutaneously stimulation, we use two needles that we introduce nerve to the nerve through the muscles and skin.
Okay. I thought it was a little bit different. So they open a slightly bit and then they put the electrode so it can stimulate. It's not like there is a circuit inside.
No, this is another procedure. So we use the device to perform this procedure.
Okay. So, but what I don't understand well is that how is it related that I understood something like this stimulation is because I don't know if it's a future work, but
Okay.
you want control when they cannot control the field or something like that.
Yeah. I'm very, very sorry, but I will have to continue. Maybe at the end of the presentation, you can talk.
Yes.
Can explain you, because we are already 3 minutes late for the next presentation. Thank you very much. Okay, let's move on to our next presentation. And it's about a novel flow meter with piezopolymer material of PVDF for biomedical applications. And it is presented by Joel Mendez Ubaldo.
Hello, everyone. Good afternoon. My name is Joel Mendez Ubaldo, and I will show you this presentation about a novel. Thank you. A novel flow meter with piezopolymer material of PVDF for biomedical applications. The presentation has an introduction, objectives, methodology, results, and conclusions with future works. Well, about the introduction, and we have two situations that allow us to see the importance develop a low-cost flow meter. The first one is about the World Health Organization. This institute includes a document on an oxygen concentrator. In this case, the document recommended research develop a low cost flow meter. What is the reason? Well, because the cost to fabricate a low cost oxygen in different countries in Africa is the same. The cost to commercial flow meter. And another situation, the COVID-19 pandemic caused a high demand for healthcare, pharmaceutical, and technological resources. In this case, this situation showed the need to develop flow sensors as well as another electronic components. And well, that could be able to meet daily needs in the medical field during the future emergencies. Both situations show us that, come back, thank you. Both situations show us that developed flow meter are essential for biomedical application. And in this paper presents a preliminary results, preliminary advancements about a novel, develop a low-cost flow meter. Next, please. Well, about the objective, we have a general objective. It is develop a flow meter using this polymer material for biomedical application. And the specific objectives are three. The first one, manufacture the electrodes that are in contact with the PVDF. The second, analyze the piezoelectric response of the material to air fluids. And finally, obtain the mathematical expression that describes the behavior of the flow meter. The next, please. Well, about the methodology, include fabrication these components in 3D printer. You can see the first one, the picture on the left. You can see a half inches diameter PVC coupling for air inlet. The second components, you can see the electrode designs with PLA material. And the third, you can see an air outlet coupling for a half-inch PVC pipe. Picture on the right, you can see the fabrication of these components. The first column, you can see the 50% fabrications of output coupling. And in the bottom, you can see the 100% output coupling. In the middle of this image, you can see the next component. Is about the 15% fabrication of input coupling. And the same, you can say 100% fabrication of input coupling. And then finally, you can see the A1 and A2 electrode, 100% manufacturing. This design is important because only side of each electrode is covered with Cooper tape because capacitor model is required. In this electrode design, include in the middle a PVDF material, and I would like to remember the PVDF material is a semicrystalline polymer, and that it has electrical properties. The next, please. Well, in this case, you can see the table about the geometry characteristics for development of the flow meter. The first column, you can see the name. The second, internal diameter in millimeters. And third, you can see external diameters in millimeters. The most important parameters of this table is contact area, because this area is about the electrodes. And finally, this electrodes has thickness 1 millimeters per one. Next. Well, in this image, you can see the the installations, the equipment consists an air compressor. The first one is an air compressor that sends air drop, and the second element is a half-inch PVC pipe. And third, you can see the analog flow meter. This instrument allows us to control the air ascent. And the fourth element, you can see the prototype flow meter. In this case, these prototypes are assembled. In its interior, you can see the PVDF. And the number 5, you can see the RLC bridge, and that measures the change in capacitance and the airflow changes. Finally, you can see the number 6 is a digital flow meter. In this case, these instruments help us to verify the principle of continuity. In other words, the airflow entering must be equal to airflow leaving. And this instrument needs a power supply. Is represented with number 7. The next, please. Well, about the results, we have the first geometry, A1 electrodes. The picture on the left shows us the different values of air. You obtain different values of capacitance. The picture on the right, you can see verify the principle of continuity. The same idea. The airflow entry must be equal to the airflow leaving. These values range from these values in picofarads in ascending flow, and from these values in picofarad in ascending flows. The working flow range was from 1 liter per minute to 15 liter per minute. The next, please. The results for geometry, the A2 electrode, picture on the left shows a variation of capacitance when the different values of air are sent. The same picture on the right allows us to verify the principle of continuity. In the case of the second geometry shape, capacitance values between these values in picofarads, they were obtained in the ascending flow, and in the descending flow, the values range from these values in picofarads. The next, please. Results about the mathematical expression. We have 2 ideas. The first one, the air force applies a mechanical stress, obviously on the PVDF, cause a variation in capacitance. And the second idea, the change of capacitance over time depends on the rate of change of airflow. If you combine this idea, you obtain the differential equation like number 1, and where you can see the variation of capacitance is proportional to variation of air, where K is a constant. This constant depends only on geometry and material properties, and the alpha is the coefficient, sensitivity coefficient on the capacitance to mechanical stress. This parameter is experimentally determined. The next, please. Remember the letter K, the constant K, related the change in mechanical stress to the change in flow. And for geometry 1, you can see this value K1 in, and for geometry 2, A2, you can see the value of K2. The next, please. Finally, well, a linear least square fit describes the relation between capacitance and flow rate. The experimental slope were this value for geometry 1 or electrode and A1 electrode, and this value for electrode A2. R squared was approximately 1 for both cases, and we have alpha with this value. Therefore, we obtain the differential model. In this case, is for A1 this expression, or for A2 and this expression. The next, please. Well, conclusion and future works. The result shows that the second geometry shape produce lower capacitance values. Is obviously is consistent with is a smaller content area with the PVDF material. And flow gain analysis revealed that the second geometry achieved better performance with approximately 19% flow gain compared to the approximately 18% for the first shape. These results indicate that electronic designs plays an important role. And additionally, well, the results indicate a higher sensitivity for electrode A1, and the geometry one is more favorable to convert chains into capacitance chains under the test conditions. The next, please. Well, about flow and pressure parameters for medical equipment, we can conclude that the flow meter could work in two devices, oxygen concentrator and speedometer, because we have the same parameters with these developed. And finally, well, the mathematical expressions we also allow us to determine the appropriate geometry for typical parameters for typical mechanical ventilator parameters. The next, please. This is my reference, and that's all. Thank you for your attentions.
Thank you, Joel. Have any question here in the room, please? Any question online, please? Okay, thank you very much, Joel, for your presentation.
Thank you.
Let's continue with our third presentation. It's about ultrasonic field evaluation through order of discretization, variation, and distribution of grid points, BEM modeling, and presents Raquel Martinez.
Good afternoon, everyone. Thank you for the presentation. Can you confirm if you can see my screen, please? And if you can hear me?
Yes, we can see your screen.
Okay. So my name is Raquel Martinez Valdez. The work that I'm going to present is ultrasonic field evaluation through order of discretization, variation, and distribution of grid points with BEM modeling. So the agenda of the presentation is the one shown here. And let's start with the introduction. Ultrasound are mechanical waves over the human hearing range that is 20 kilohertz. And typically, medical ultrasound applications are developed in the range from 1 megahertz to 10 megahertz for diagnosis, physiotherapy, and thermal ablation. In thermal ablation therapies, in thermal ablation, so ultrasound beam pattern can be modified to focus the energy through concave monoelements, acoustic lenses, phase control arrays, and this modification forms a convergence or makes the beam path converge in a focal region that is typically ellipsoidal. And after that region, the beam pattern diverges. So in the focal region also, there's a maxima of acoustic pressure and also acoustic intensity. This characteristic allows or is an advantage for focus ultrasound for the treatment of benign or malignant tumors. It's a non-invasive non-invasive technique that uses ultrasound or magnetic resonance imaging for planning and delivering the treatment. In the focal region, there's a quick temperature elevation over 56 Celsius, producing coagulative necrosis in short times. Modeling is a tool that allows us to obtain an estimation of the behavioral phenomena, in this case, ultrasound. Commonly, finite element method, FEM, is used to model the ultrasonic propagation in a finite domain that needs to be discretized with a frequency-dependent mesh that, at least for acoustic problems, have to be 10 elements per wavelength. Limitations that present the FEM modeling are when the models or the geometries are large and high frequency problems like 3D models. We are now exploring a different method that is called the boundary element method, that it only uses surfaces or boundaries that need to be discretized and in an infinite domain. It can solve the acoustic problem in that sense without meshing all the domain, a finite domain. On the other hand, it has a problem with multi-domain because it only solves the scattering effect around or over the surfaces. The objective of this work was to evaluate the resulting acoustic fields produced by a transducer with cylindrical section geometry with a symmetry plane after varying both the order of discretization of the dependent variable, that is the acoustic pressure, and the distribution of the grid points used to calculate the acoustic field. So we propose this geometry that is a demi-cylinder or section of a cylindrical shape. In this case, this boundary is a transducer that has a radius of 15 millimeters and a height of 6 millimeters. It has a symmetric plane at y equals 0, so we can reduce computational cost. And the two conditions that we wanted to analyze in this work were the order of discretization of the pressure in a linear, quadratic, cubic, quartic, or quintic shape, and the distribution of the grid points used to calculate the ultrasound pattern of field in distribution uniform or mixed, that is formed with uniform and exponential distribution. The governing equation for BEM modeling are the Helmholtz equation in the frequency domain, are shown here, 1, 2, and 3, that it states that it requires or could be added a background pressure wave, complex behavior of density, and also a speed of sound. But in our case, we are not using complex values, and also we are not using a background pressure. So the equation is reduced to this one that is usually used in FEM modeling for time harmonics models or frequency domain. The boundary condition of the model were acoustic pressure in the surface of radiation, this one here, with an arbitrary value of 500 PA, the plane symmetry at y equals 0, the domain, infinite domain that surrounds all the surface has acoustic properties of water, and the operating frequency for all models was 1 megahertz. The boundary was meshed with 10 elements per wavelength, resulting in this quantity for all cases. Also, in a post-processing stage, we need to define infinite domain bounds or the volumetric bounds where we are going to calculate the acoustic field inside, for example, this box. So the infinite domain for the x-axis was from -10 millimeters to 10 millimeters, for y from 0 to 10 millimeters, and for z from 0 to 30 millimeters. Also, in this box, we need to define how many points or grid points we are using to calculate the acoustic field. So we use 201 points in each axis, in this axis, and the distribution of these points were uniform or mixed. That console makes it automatically. So here are the results for the order of discretization. We had these five cases: linear, quadratic, cubic, quartic, and quintic. These are for the pressure acoustic that we are solving in the boundary of the transducer. So as we see, it's evident that as we increase the order of discretization, the degrees of freedom also increase, the solution time increases, and the computational resources increase too. So after having these solutions, we need in the post-processing stage to calculate the solution for the acoustic field for the uniform and the mixed distribution. So there were 10 solutions of acoustic pattern. As a continuity of a previous work, we had modeled that same geometry, and we used a quadratic discretization order and a uniform distribution of points. So we use those results as reference to calculate the differences between the amplitude of the pressure. So in here, we see the pressure distribution along the z-axis, and there is no visible, to say, there's no, well, I can see, there's no visible difference between one shape or another, or one solution or another. The 10 solutions are overlapped. So we took the difference in pressure amplitude by taking as reference the quadratic uniform solution, just to amplify or to better see the distribution and the differences in pressure along the axis. And here in this point, and C equals 0, we have a difference in pressure lower than 10 PA, and at the focal point that is 15 millimeters, we have a maximum difference in pressure of 8.37 PA for the quintic solution. Also, I don't know if you can see that these lines kind of seem like dashed, but also continue. Well, that is because the solution for this one, that is the linear, the uniform and the mixed solutions are overlapped. The same occurs in the other solutions. Then, in the J and the Y axis, we have a different distribution across the focal point. In here, it is also not possible to see visually see like the difference in amplitude of the pressure. But in here, I don't know if you can see that there's a little shift or displacement in the valleys or the points that go down to 0, and also in these parts that form the main lobe. Also, there are differences in the amplitude. So this is what we are seeing here. By taking the difference in pressure amplitude, by using as reference the quadratic uniform solution, these 2 points, have the maximum pressure difference close to 211 PAs and are located around the limits of the main lobe. Also, we can see that for the cubic, quartic, and quintic solutions, the variation of the pressure is higher along the y-axis than in the case 1 and 2 that are almost zero, for exception of the focal point that for the linear, uniform, and mixed solutions there's a difference in the amplitude. And in the x-axis, there's a different pressure distribution that we can see here. Again, the 10 solutions are overlapped, so there's no visibly a way to see the changes in pressure along the axis. By making the pressure difference, or by taking the difference in pressure, we can see that the maximum pressure difference was around 20 PA for the quintic case. Also, well, we use these maximum values in each axis, this one and this one, to try to better view or analyze the difference between the solution by normalizing the solutions. So here are the results for those normalized values. In here, it is possible to see that the solution 2, as we said, is overlap the mix with the uniform, so there is no difference in here. It's in the zero base. But for the other, for example, the cubic, quartic, and quintic, the pattern or the beam pattern remains practically the same, just changing a little bit the amplitude. But in the linear one, there's a shift of the point, of the focal point. Here we can see also that for the linear and the quadratic solutions, the difference is almost zero, exception for the amplitude variation that is in zero. Still, for all solutions, most of the variations are lower than 0.2. So as we need to make more numerical experiments to establish the order of discretization and the quantity of grid points. Also, we need to establish an adequate number of grid points containing the volumetric bounds, and following a convergent analysis, we notice that there is no change in the acoustic field when using a uniform or mixed distribution of grid points, and the order of discretization, the number of grid points, and its distribution should be considered in accordance with the computational model in development. As conclusion, we have that the maximum absolute difference in average at the focal point was 6.53 PAs in the quintic solutions, that is a relative percentual error of 0.23. The larger differences in pressure amplitude were observed in the y-axis at the minimum pressure values, which correspond to the lateral lobes formation. And by using a quadratic order of discretization and a uniform distribution of grid points, the solution time was reduced without compromising the results. Thank you all for your attention.
Thank you, Raquel, for your presentation. Let's see if we have any questions here in the room, please. No? Questions online, please. Okay, so thank you very much, Raquel, for your presentation.
Thank you.
And we can continue with our fourth presentation, which is sensor-based Mexican Sign Language recognition using machine learning, and presents Valeria Ramos Vázquez.
Thank you. My name is Valeria Ramos Vázquez. I'm a biomedical engineering student here in the National Polytechnic Institute here in Mexico City. Today, I'm very excited to present to you all the project me and my team have been working on for the past year, which is a sensor-based Mexican Sign Language recognition system that uses machine learning. To start, I would like to give some context in projects that have been done globally over the years in sign language recognition. When we look at globally the research that has been done, we can see that the majority of them are either in Chinese Sign Language or in American Sign Language. This given, of course, the population and the technologies that they have over there. What we don't find, however, in this pie graph is the Mexican Sign Language translation systems. So when we look at the state of the art here nationally, what we find is that the projects that have been done have been limited to only translating either the alphabet or they require a camera and then recognize it by image processing. So what we wanted to do in this project was to apply the technologies that have been applied globally and take it to Mexican Sign Language, given that this sign language is obviously different from the international ones and it has its own rules and grammar. So what we decided to do was apply these technologies to be able to translate signs into spoken language instead of the alphabet, which is obviously a more natural way of communication for the people that use this language. To do this project, we divided in 3 phases. The first of which was to select which words or phrases we wanted to translate with the system. After that, we move on to phase 2, which is the hardware development and the prototype. And finally, phase 3, which is the software development. To start with phase 1, as I mentioned here, we selected the gestures, so the words and phrases that we wanted to translate. To do this, we got in contact with an organization here in Mexico called BIO4. They were kind enough to talk to us about the project, and they told us that to be able to translate correctly the words and phrases, we had to select a selection of commonly used words that could be universal about in all of Mexico, so it wouldn't vary region from region. And then after getting that information from them, we corroborated ourselves with a dictionary that's submitted by the Mexican government. In this case, we used Manos con Voz, in which we compared the information we got from the organization and we made sure that we were doing the words and the phrases correctly when recording. Here we can see an example of how we divided these gestures. We actually decided not to translate whole words or sentences. We decided to segment these into what we call gestures. So the gestures we defined ourselves, and we defined them by 3 key points. The first one being hand position. Here we see it's the letter D in the alphabet. We also have it accompanied by a picture. We have an initial position of the hand, and we also have the movement that follows it. And this is how we define the gestures. What this leaves us with is with 13 gestures that we decided to use to test the system. Here we can see the gestures, the Spanish meaning, and the English translation. What we got from this was actually that we could combine these gestures to make new meanings or to make phrases. So as we can see, for example, in the second table, the first one says good morning, which is when we combine good and day. But what's curious about Mexican Sign Language and the context of it is that we can have singular words that have one meaning, but when we combine them, they have a different one. So for example, here we see gestures 5 and 6, which means with and to be. But if you say with to be, it actually means how are you? So we were able to also make that happen by joining these together in the system. So for in total, we had 17 expressions, the 13 gestures that the system recognizes by itself, plus 4 phrases that we tried out in combination. Now moving on to phase 2, now that we had the words and the phrases that we wanted to translate, we move on to building the hardware and the prototype to be able to register these signals. To do this, we decided to use a glove. And in our glove, we decided to place 5 inertial measurement units. In our case, we used the NPU 6050. And as well, we can observe here, we use a multiplexer. In our case, the TCA 9548. This to, of course, make sure the signals were able to go into our microcontroller. Here we can see a picture of our final equipped glove in the dorsal view. This is the one we used for our project. As we can see here, we have the 5 sensors in the distal phalanges of the hand, as well as the multiplexer, and the cables that you see there actually go to our microcontroller. In our case, we decided to go with the STM32F4. After we had the hardware to be able to register these signals, we then move on to the software development, which includes the signal processing as well as the development of our machine learning algorithm. To start with this, we decided to create a acquisition protocol for the data set we were going to use for this system. So to start, we first had to teach our test subjects these gestures that we limited before, right? So for our case, we used a 24-year-old male as a test subject to do all these gestures. We first teach him the gestures, then we put on the glove and our prototype. Then we do a trial run to make sure the signals are being registered correctly. And after that, we start to register gesture by gesture. And then, of course, store it into our data set. Here we can see the specifications for the final data set we achieved. We had a total of 80 samples per gesture, so 1,040 samples in the data set. And we decided to do a sampling frequency of 250 Hertz, which gave us a vector size of 1,000. After we had our data set completed, we then had to filter it because we noticed that we had some high frequency noise in the signal. We decided to go with a low pass digital filter, in our case, one that was for 5 Hertz, and we went with a 4th order Butterworth filter. Here we can actually see the before and after of the processing of our signal. Here we can see one sensor for one finger. In this case, it's the 4th, it's the index finger. We can see here that the NPU 6050 gives us both the accelerometer and the gyroscope in the X, Y, and Z axis. And we can see here the noise that we had before was reduced. And what we were left with was the overall shape of the graphs, which is what we really needed to be able to later be able to recognize these gestures and differentiate them. We can also observe here that the time we had for each gesture was 4 seconds long. We did this on purpose, so each vector would be the same size. With the sampling frequency rate of 250 Hertz, we had a vector size of 1,000. Now that we had all of our graphs filtered, we then went on to extract features from them. So we decided to do bi-axis, X, Y, and Z for both accelerometer and gyroscope, but also we decided to use the 3D vectors that were produced from this. So we actually also used those. And for both of them, we applied mean, standard deviation, root mean square. But for the 3D vector, we applied also signal magnitude area. So what that gave us at the end was 13 features per accelerometer and 13 features for gyroscope per finger. By 5 fingers, we have a total of 130 features. So a vector of 130 that represents a whole gesture for the whole hand. Now that we had these representative vectors of each gesture, we then move on to choosing a machine learning model that could recognize and differentiate from these. So we actually tried out 2. We tried out k-nearest neighbors with 3 neighbors. And we also tried out random forest, and we used 100 decision trees. What we found out by comparing these models was actually the following. And when we did the offline testing, we did a 70-30 split with 70 for training and 30 for test. Here we found that curiously, the k-nearest neighbors and random forest had the exact same accuracy. It was 99.68%. However, the main difference between them, as you can see here, is actually the inference time. We can see that the k-nearest neighbors ones is almost 10 times slower than the random forest one. And given the purpose of our project and that we wanted to have the most immediate translation possible to voice, we decided to go with random forest, given the speed and the velocity of it. So once we chose random forest to apply to our algorithm, we now had to make it sure it could be embedded into our microcontroller to make this an embedded system. So what we did was followed this protocol, which basically means that we originally programmed our code in Python. We had to pass it on to C, so then we could actually put it into and load it into the microcontroller, which, as I mentioned before, was the STM32. So we used the SC microelectronics tools that they provide to do this. Here we can see the online or live testing results with this. So for the live testing results, our subject performed 260 tests, so 20 per gesture. Here we can see that the live performance results are 91.9% accurate, with gestures varying from 100 to 90% accuracy approximately. Finally, we can conclude from this that the separation of the gestures that we did at the beginning to be able to segment these words and phrases actually helped us later in the dataset protocol to be able to standardize these and make sure that the machine learning algorithm could be able to recognize them. We also did the comparison between two different machine learning models to be able to choose which one would be better for our purposes. And finally, we can conclude as well that there was a successful translation into spoken language. I would like to thank you all for your attention and also give special acknowledgments to, of course, Latido Sordo, which was the organization that gave us the information to start this project, to the National Polytechnic Institute for giving us the facilities to do it, and to our work team, which is here present, the doctors and my partner. Thank you.
Thank you very much, Valeria, for your presentation. Let's see if we have any questions here in the room, please.
Yeah, sorry, I'm not totally sure why do you combine English and Spanish in the same language? Why do you combine this English and Spanish?
Oh, we didn't combine them. The system is intended for Mexican Sign Language.
Oh, yeah, yeah.
So sign language varies country to country, you know.
Yes.
American Sign Language is different from Mexican Sign
You
Language.
use Spanish.
So yeah, of course. So what we have here is that there are many projects that have achieved this.
Okay.
For example, in the US and in China, as we showed in the pie graph, there are many projects that have done this. The difference is that Mexican Sign Language has its own structure.
Yeah.
And because it is different, you can't directly apply the technology to our language. And because there aren't many projects available right now here in Mexico, that's just what we did. We decided to apply technologies that had been applied before, applied it to Mexican Sign Language, and we got good results.
Okay.
Here we have the translation just for the conference.
Okay, thank you.
Thank you for the question. There's another question, please.
In the slide 20, please. Yeah. What is the principal difference between the KNN and the random forest? Because you decide for random forest, but for what?
Yeah, it's mainly the speed. When we were looking at the system afterwards, we did trial runs with, for example, just one gesture to see how fast it would recognize them. And of course, we didn't calculate for the whole data set. But when we actually found the answers, because we wanted to bring it to voice, we really wanted the sign to be made and then almost immediately to have the voice speak what the person wanted to say. So when we look at these times, obviously thinking and scaling the project larger, adding more words, adding more phrases, we want to make sure that the algorithm that we're using is the fastest possible one.
Yeah, you need the fast. Yeah, but the in hardware.
Yes, in hardware to apply them.
And this is I don't know, difference between the KNN and random forest, but in hardware.
We didn't put the KNN algorithm to the embedded system. After we saw the offline performances before, we then decided to implement the random forest algorithm into the microcontroller.
Yeah. Okay. Thank you.
You're welcome.
Okay.
Yeah,
Yes, please.
Okay, thank you for your presentation. It was amazing. I would like to know if you try K4 cross-validation or why did you choose to just train with 70%, and if you did it like that, did you try multiple rounds or how did you do that part?
The split we did for 70-30, and most of the technologies and the things we chose were based on the state of the art. So we looked at many papers from ASL and CSL, Chinese and American, and we found that this was the standard as well as the KNN and random forest. We chose those two as well because they were the ones that had the best results. So we decided to apply that as well.
Okay, thank you.
Any other questions? And you mentioned that you want this immediate response. What do you mean with immediate? How long does it take after you finish the gesture? How long does it take to give the response in voice?
Right now, our system is in the first stages. This was made, as I said, in the last year. So right now we're doing trial runs just with the computer. Right now, there's an inference time that we ourselves added because of the joining of the words to create phrases. So we gave like 3 seconds for a button to be pressed and for it to be joined. So there's a little extra time because of this time that we give extra for the person to give another gesture. But after that time is done running, it takes approximately a second or less than a second.
Yes. Okay. Thank you, Valeria. Do we have any question online, please? No questions? Okay. Okay, let's continue with our next presentation. And it's about biomarkers for stress and sleepless evaluation. And it's presented by Diani Donati Delphi.
Thank you very much. Hi, good afternoon. I'm glad to see you here. My name is Diani Delphin Garcia. And with my coworkers, I realized it takes only 1 second to have an accident. And we have all been here. For example, how well we have slept at classes, or what about behind the wheel? And this seems worst when there is a lot of traffic, so it can take a real risk. That's why we realized this investigation, and what we are going to see today is about stress and sleepless in human performance. Then I'm going to explain you about the protocols and signal acquisition we made. The results, we are going to see the main outcomes across these protocols we realized, and then conclusions. Stress and sleepless are two conditions that affect human performance, especially in situations that requires high cognitive and physical demands. For example, attention, decision-making, and reaction time to stimuli. There are some human signals that can give us an insight to how we react, for example, heart and our sweat. And early detection can contribute to better understand this and propose intervention strategies. So we realized two different protocols. The first one was a virtual driving protocol in a simulator. And then we realized another protocol called physical exercise. They both have the same condition. We made them under rested condition and in sleepless restricted condition. This means the participants only slept between 3 to 4 hours the night before. So how we acquire these signals? First, we use unicorn hybrid lab. This is an electroencephalogram that consisted in 8-channel CAP. And we also use Kenshin Suritsu, a prototype realized at Laboratorio de Instrumentación and Procesamiento de Señales in UPITA. This prototype gives us photoplethysmography information and electrodermal activity. Why we use this equipment? First, the electroencephalograph gives us electrical activity, and Kenshin Suritsu helps us to have information about our heart, and electrodermal activity gives us information about tonic and phasic response. For the first protocol, we made it in the simulator. The route consisted in 90 minutes route. We only use a male and a female subject. This protocol was approved by the Ethics Committee of Escuela Superior de Medicina, and it consisted in a monotonous highway under 3 different conditions. The first one was during raining conditions, the second one during dry pavement, and the third one during wet pavement. Remembering, we realized this under rested condition and sleepless condition. How do we process this signal? First, we remove the outliers, then we detrended the signal, so we eliminate the slow varying fluctuations. We filter it with 2 different filters. The first, 5th order Butterworth, we cut off frequencies between 2 to 38 Hertz. Then a 4th order Chebyshev type 2 under cutoff frequencies from 4 to 30 Hertz. We then realize power spectral density using the Welsh method, and we made an estimation of the area under the curve with the trapezoidal rule. Then we extract energy frequency bands, theta, alpha, and beta. And why do we need these frequency bands? Because we investigate and found that with these bands, there were relations made that give us a knowledge about how this, what activity the brain has. And we compare, well, with these frequency bands, we use them to compare them between the different states, rested and not rested condition. For the second protocol, 8 young adults realized the protocol. We made a SF36 health survey questionnaire, and this protocol consisted in progressive increasing difficulty. So we have these events. We made them rest for 3 minutes, sorry. Then they realized 10 squats. Next, they rest for 1 minute. Then they realized 10 jumping squats. After this, they again have a rest of 1 minute. And finally, they realized 10 jumping squats plus 5 seconds of isometric squat and a rest of 10 minutes. We pre-process this signal. First, we remove 10 seconds to the equipment for stabilization. Then they detrended again to eliminate the slow varying components. We rescale this signal to change our ADC values to real world. Then we filter, but we use different filters. For photoplethysmography, we use 2nd order Butterworth with cutoff frequencies from 1 to 167 Hertz. And for electrodermal activity, a 2nd order Chebyshev type 2 from 0.05 to 0.37 Hertz. Then we segment it to identify the different events made, and we extract the features. So we have heart rate and electrodermal activity with tonic and facet. And we use this to, well, when we are in a pipe room relaxed, we have from 60 to 100 beats per minute. When we make exercise, this comes up, and when we sleep, they comes down. Another electrodermal activity makes the same. When we are like rested, the activity comes down, but here the signal separates into 2. So this gave us information about our reaction in the body. In both conditions, sleep and not rested. And the results were, for example, in electrodermal activity, we realized Tukey's and Dunn's comparison test, and we found out that the activity was concentrated in low varying channels and in posterior ones. For example, lower values in anterior channels in a sleep state and higher values in posterior state. Let's see this image. So This line is the line that will give us information where our anterior channels and our posterior channels. We can see that in rested and sleepless condition, for example, for FS electrode, rested condition is higher than sleepless condition. But at the other hand, in posterior channels, for example, in PO8 for rested condition is lower than in sleepless condition. So this was an interesting finding for us because, well, we were not expecting this. That was for the first protocol, the one that is in the virtual driving protocol. And in the exercise protocol, we realized Tukey's comparison and two-way ANOVA, and we were expecting differences between states, between rested and sleepless, but we didn't find any differences there, but we found that the differences were between events. When we realized higher or increased the difficulty, the changes were notable. So yeah, we conclude that EEG showed that energy for sleepless was concentrated in posterior channels than in anterior channels, and in physical exercise protocol, photoplethysmography and electrodermal activity showed no significant differences between events. Thank you very much.
Thank you, Lenny, for your presentation. Any question in the room, please? Yes, please.
Congratulations for your project. And I'd like to know if, well, did you consider the diet of the persons you use?
Like their
They eat normal?
Yes, well, the participants have like the same range ages, and as I told before, we realized the SF36 health survey questionnaire, and that gives us an insight to their habits and lifestyle. Now you're up.
Okay, thank you. Any other questions here in the room? Yes, please.
Very, very fast question. At what time after the night were done your protocols?
The 4 hours.
4 hours after the.
They slept the night before between 3 to 4 hours, and then they have slept like 1 hour or 2 hours, and we realized the protocol.
Okay. Do you think that if you waiting for more time, your results are different or not?
Maybe because they have been awake for more time than the time we really made it.
Yeah.
I have a question.
Yes, please.
There were 8 volunteers, right?
Yes, for the exercise, yes.
All of them, they had similar results, or some of them had any anomaly, especially in the statistics?
No, they have similar results. We think because they are like in the same ages and have like the same lifestyle.
In such way, what was the exclusion criteria for the volunteer?
Being like for 30 years over, if they didn't realize like the different conditions, if they, for example, slept more than we tell them they have slept,
Less than 19.
less than 18 years, yes.
Okay.
For the drivers, did it matter how long they had been driving or if they were new drivers?
No, the route consisted, it was the same route and consisted like in the same stages, 90 time in total. There was no longer near lower time.
I'm referring to like the experience of the driver.
Okay, yeah, one of the requirements, we asked them, well, we're the two participants, one male, one female, and they have both like 2 years of knowledge about driving.
Do we have any question online, please? No? Okay, thank you, Vianney, for the presentation. Okay, now let's move on to our last presentation. And it's about predicting neurological recovery after cardiac arrest using MLP and histogram-based RR interval features, and presents Sebastián Loesa Jiménez.
Okay, so hello everybody. I'm here to talk about the research I made in collaboration with Dr. René Luna Garcia and Dr. Blanca Tovar Corona during this year about predicting neurological recovery in post-after cardiac arrest using MLP and histogram-based RR interval features. So to understand why this investigation or research is relevant, let's begin with the global and clinical context. So the World Heart Federation mentions that cardiovascular diseases are remain a leading global health challenge. And during the last 30 years, the deaths caused by cardiovascular diseases have increased, especially in low and middle income countries. And the World Health Organization mentions that in 2022, cardiovascular diseases caused 19.88 million deaths, with 85% of these fatalities resulting from cardiac arrests. Now, despite the advances in resuscitation techniques, the survival rates for cardiac arrest are very, very low. They are below 10%, and many survivors suffer from severe neurological damage due to prolonged cerebral hypoxia, which means that the brain is, the brain remains a period of time without oxygen. And when a patient gets into the hospital in coma, they get into the intensive care unit, and the physicians must rapidly assess the prognosis of the comatose patient. This is very, very important because a poor prognosis could lead to the withdrawal life-sustaining treatment, which means that the patient could be disconnected and lead to its death. So there's a critical need for precise data-driven tools to support prognosis and avoid premature withdrawal life-sustaining treatment decisions. So the objective of this research is to develop a classification model that predicts the neurological prognosis, which is good or poor, of post-cardiac arrest patients using electrocardiograph recordings, contributing to more accurate and accessible prognosis assessment in intensive care units. So now let's talk about the methods and materials, what we did and how we did it. For the data source, we selected the George V. Moody FissionNet Challenge of 2023 dataset. This database contains electroencephalograph and electrocardiograph recordings for more than 1,000 patients collected by the iCare Consortium. It is important to mention that each case was previously labeled with good and poor outcomes. And we selected a subset of 137 patients, where 59 were good and 78 were poor. The sex distribution we get was 92 male. For females, the average age was 59.8 with a standard deviation of 17 years. The signals we used was, we only used electrocardiograph recordings. We only used one single channel to process this data, the ECG-L, which is the left channel of the heart. The sampling rate was 512 hertz, and the recording segmentation is 1 hour files per patient. This means that if a patient was 72 hours in coma, we had 72 different files. Not all the patients had the same number of hours. There were patients with 72 hours, 6 hours, 14 hours, and this depends on the evolution the patient had, right? if he survived, he recovered, or he didn't, or she didn't. So now, talking about the preprocessing of the data, first, we can see here in figure 1, the electrocardiograph segment of 10 seconds for the second hour of the patient 286. In this electrocardiograph segment, we can see there's a lot of noise in this electrocardiograph signal. So this is why we decided to apply the Butterworth bandpass first order filter between 5 and 15 Hertz. And after doing this, we get the second pulled image in the figure 2, which is the filtered electrocardiograph signal. We can see it's clearer. We can get more data, or we can process it in order to avoid adding bias to the model. And we decided now to make the Pan-Tompkins algorithm. This was made with the intention to detect the R peaks. So the R peaks are like the red points. And these are like the higher parts we can see in an electrocardiograph signal. We made this with the intention of calculating the difference between R peaks. So because we realized that the more difference between these R peaks, it was going to be more probable to the patient to get a poor prognosis. So we started saving these differences in an array in Python. And then we proceed to make a histogram. We can see the RR interval duration in milliseconds. We also normalize the frequency. This was with intention because not all the patients have the same number of hours. So the histograms were going to have like different forms, and they were going to be very disbalanced. This could add some bias to the model also. And well, after normalizing the frequency of this histogram, we tried to model this distribution. We tried to model the distribution of the histogram with a composite Gaussian exponential model. This composite model is composed by two Gaussian and one exponential. And we did this because we wanted to capture both regular and irregular heartbeat dynamics observed after cardiac arrest. And well, in figure 5, we can see how every component ported something to the total fit, which is plotted in the red spotted line. So, for example, we can see how the black line, which is related to the second component, to the second Gaussian component, upwards something to the total Gaussian, which is the yellow, as well as the green one, which is related to the first Gaussian component, as well as the exponential component, and how the total fit models or adapts to the distribution of this histogram. Well, it is also important to mention that when we model this fitting, we calculated 9 parameters, which are A1, A2, A3, mu1, mu2, B, sigma 1, sigma 2, and C. And these were the input features for the neural network classification model. We used a multi-layer perceptron, which we use these input features, the nine RR interval features I mentioned. We used 3 hidden layers of 128, 32, and 64 neurons each. The activation function was the ReLU, the rectified linear unit. The output activation function for the output neuron, was the sigmoid for binary classification. We used the atom optimizer, the binary process entropy for the loss function. We trained this neural network with 1,000 epochs, and we divided the tests. We divided the subset into train and test split of 80 and 20% each set. So let's talk about the results and the discussions. The results we got. In the figure 6, we can see the confusion matrix, which was made to the test set. And we can see that out of 16 patients with poor outcome, 14 were correctly classified, while 2 were misclassified. And for patients with good outcome, 7 were correctly classified, while 5 were misclassified. So we can see here like some performance metrics. So let's remember that precision tries to reduce the false positives error. We get for the poor class a precision of 0.74 and for good class 0.78. For the recall, let's remember that tries to reduce the false negatives error, which we had for poor class 0.88 and for good 0.58, which is very low. For F1 score, for poor class, we had 0.70, and for good class, we had 0.60, and specificity, we had 0.88, which also tries to reduce the false negatives error. So, well, the model shows promising predictive capability for poor outcomes. However, we still have a critical issue in reducing the false negatives problem, which is the most dangerous type of error, because this means that the patient gets a poor prognosis when he's actually going to have a good prognosis. So we disconnect the patient and it could lead to his death or her death. However, we get this due to two factors, or we had two important limitations, which were that the model was trained on a MacBook Air M2 with 8 GB of RAM, which didn't allow us to process the complete data set, which size was of 1.5 terabytes. So for the future work, we could recommend to increase the dataset size to improve class representation, which is related to the third point, which is leverage cloud or high performance computing resources to train the complete dataset. Also apply data augmentation to enhance variability and robustness. And that would be all. Thank you for your attention.
Thank you, Sebastian. Any questions here in the room, please?
Yeah, when you present your matrix, vision matrix,
yes,
check because the good and poor in predicted is very similar. In predicted and good and poor is very similar.
Yes.
Yeah.
Yes.
Because I check your future work.
Yes.
You present the in the middle point data augmentation.
Yes.
But if you use data augmentation with this value with your database, maybe yeah, maybe it's not a good idea to apply to data augmentation with this matrix.
Okay.
Because and I have a question for you.
Yes.
What is your opinion about the 2022 was a good year for your work? In the slide 3.
Yes.
In the slide 3, you mentioned that the 2022.
Yes.
But what is your opinion about the 2022? Because for your work was a good year in 2022.
Well, could you explain why it was a good year?
Yeah, because
it's related to the pandemic.
Yeah.
Okay.
Yeah.
Because this year was a good year for your work.
May I?
Yeah.
If you see statistics in cardiovascular diseases, yes, well, the pandemic was an issue, but it didn't affect as much as to consider that COVID affected specifically cardiovascular diseases. Cardiovascular diseases have been the leading cause of death in the world, and it didn't change during the pandemic.
Yeah.
I mean, even with the pandemic or without the pandemic, cardiovascular diseases have been increased, and well, it was not exactly because of the pandemic, this reason. Maybe, well, yes, presenting 2022, because there's no actual data about this statistics. But if we see the year-by-year statistics in the National Institute of Cardiology, for example, we can see that it wasn't that specific problem in the pandemic and related to cardiovascular diseases.
But not only the heart problem. Maybe in 2022, with the last work in 2022, increase the anxiety.
Oh, yes.
It's maybe check what happened in this year.
Yes, thank you. Thank you for the comment. Yes, do we have any other question here, please? Yes, please.
Perhaps it may be a controversial question.
Yes.
But a familiar of mine who's medic, today's medic today, progressive, someone's medic, told me once that, especially in pandemic, most of the diseases were categorized as cardiovascular. I don't know if really was for change the statistics of COVID deaths. But also he explained to me that most of the time when there is a disease and the patient died, naturally, most of them die for cardiovascular disease in such way that there is a heart attack. So I don't know if the statistics may be, I don't know how to say in English, sesgado, but how do we know that in PhysioNet, I mean, maybe the authors explained that in this database, they are specifically of a heart disease and not a consequence of another kind of disease.
You mean about the database?
Uh-huh.
Well, the database had been recorded for a long time. It wasn't in 2022. So no, I mean the database is not related to pandemic problems because it was a long time that was taken for the recordings.
Okay.
Was not exactly 2022.
Okay. It was not related. I thought it was.
No, because it was a long term in which the database was made.
Okay. Can I ask a question? So you speak about, for example, you give an example about if there was a person of 72 hours, he would have 72 records. So different patients had different records. It means different patients had different long vector size, right?
Yes.
This may cause the results you had in terms that you express that there are poor results and there is a perspective for fixed, or is independent. I mean, for each patient, there is a correct classification.
Well, for example, we had like, if a patient had 72 hours, we had like 72 vectors, but we joined the 72 vectors in order to get like one very huge vector. And then we made the processing I mentioned about, well, first applying the word bandpass filter with first order. Then we apply the band-dumping algorithm. And then we, after getting the parameters, the 9 fitting parameters, we apply the neural network. So, for example, in order to answer this question, I would consider that it's independent. So also it could be, in order to improve these results, we could also like apply, apply the complete data set. Also, I think trying another algorithm or more complex, adding more hidden layers probably could help. Like try to play with the hyperparameters of the neural network. Could also like work.
Sorry, just my concern was, for example, being more specific, the first layer of your CNN, it was the first CNN was different for each patient, or it was your whole collection that inserted to the CNN?
It was not a CNN.
Sorry,
it's a multi-layer perceptron.
Sorry, right. That's.
Yes, I think we do not have the answer to your question because we should have tried different number of hours for all the patients. For example, try to make the first 6 hours or the first 12 hours for all of them, and see if there was a different type of response because each patient has a different way to. For the evolution is different. So I think in the way that we did it, there's no response for your question.
Okay, yeah. Especially because different patients may have different patterns. I don't know.
Exactly.
Yeah. Thanks.
Any other question here? No? Okay. We have any question online, please? No? Okay. Thank you very much, Sebastian. Well, with this presentation, we close this BIO4 session. Thank you very much for being here, and thank you for coming to this conference. Thank you all.